All right, so we want to give some context to the dot product and the cross product. Okay, so we're going to start with the dot product. And so even though you may have seen these symbols before, okay, the dot and the x, these are not just simple multiplication operations when you're applying them to vectors. Okay, so with that in mind, these have very specific meanings when you're applying them to vectors. So for the dot product, okay, what this means is, what I'm going to do is I'm going to take my x components of my two vectors and I'm going to multiply them together, and then I'm going to add the y components, or the product of the y components, and then I'm going to add to that the product of the z components if there are any. Okay, and so the result is a number. Okay, and this is also a scalar. There are no units, there are no unit vectors. There are still units associated with the dot product, but no unit vectors. Okay. Okay. So, this is just how to compute the dot product. Okay. Now, this tutorial is not going to go into what exactly the geometrical interpretation of the dot product and cross product are. I'll save that for your Calc 3. But we will be using these two operations in the course of the material, so we at least need to know how to use them. Okay. So specifically with the dot product, we will see the dot product with operations related to things like work and so forth. So we will want to know how to approach these things, right? So a second interpretation of the dot product, because the dot product gives you a scalar, okay, the dot product has a second interpretation. Or not a second interpretation, but a second way of actually calculating it or thinking about it, okay? The dot product can also be computed by finding the product of the magnitudes of A and the magnitudes of B, and then multiply those by the cosine of the angle between them. Okay, so what we usually do is we usually use these two definitions in conjunction with each other to find the angle, okay, between the two vectors. Because two vectors can live in any given plane and they can have any given orientation, it's often advantageous to use these two definitions in conjunction with each other to find the angle between them. And to do so, all you would do is take the cos inverse of the scalar result of A dot B divided by the magnitudes of A and B. Okay, and we'll see how to work this out. All right, we'll see how to work this out here in just a moment. Right. So let's do an example here. So let's let vector A be the vector 2i plus 0j, right? And vector B, let's let it be 2i and 2j. Now for the moment we will just reserve these as two generic vectors. So I don't really care what units they have, but we will do something with them here. And so let's make a coordinate system. Whoop. Okay, so let's say that this is 1, 2, 1, 2. Okay, so then vector A is going to be this vector right here, and vector B would then be this vector right here. Okay, so if I want to compute the dot product between these, very straightforwardly, the dot product would be calculated as, if we go back to this slide, my x components multiplied together, then my y components multiplied together, and then the sum of those. So this is ax, this is your ay component, this is bx, and this is by. Okay, so I'm going to have 2 times 2 plus 0 times 2. Okay, so the result of this dot product is just 4. Right, the result of this dot product is just 4. And so now I'm interested in the angle between these two vectors. Okay, I'm interested in the angle between these two vectors. Now, if you're astute, you already know what the answer is. You know that this should be a 45-degree angle. Okay, so what we want to do is prove that this is a 45-degree angle using this definition, which we just calculated, and this definition, which we're going to use. So what we want to do now is say, okay, now I need to calculate the angle, which will be the cos inverse of A dot B over the magnitude of A and the magnitude of B. So now I need to calculate magnitude A and magnitude B. Well, magnitude A is going to be a really simple calculation, but both of these are going to be found from the Pythagorean theorem. And so then this is going to be 2 squared plus 0 squared, square rooted, so this is just 2. So when you have a vector that lies along an axis, it's that the length is just the magnitude. B is a little bit more sophisticated though, because it has components along both axes. So we will need to compute the Pythagorean theorem from both of its components, squared and summed and then square rooted. And so this is going to be 4 plus 4 is 8, so this is 2 root 2. And if you remember your trig, you could have gotten there pretty quickly, right? But this is 2 root 2. Okay, so now we want to plug these values into our formula for theta. So we already know the result of A dot B. That's 4. And the magnitude of A is 2. And the magnitude of B is 2 root 2. And this is the same thing as the cos inverse of 1 over root 2. And indeed, that becomes pi over 4. Which is 45 degrees, which agrees with our statement earlier that this should be a 45-degree angle. Okay, so you can use both of these ideas or definitions to compute the dot product. If you already know the angle, then you can use this definition, or if you're given the components, you can use this definition and then compute the individual magnitudes and use it in conjunction with this definition to find theta. Okay, so that's the kind of idea there, right? Now for the cross product. All right, so the cross product is a little bit trickier. Okay, so again, without going into why this works the way it does, we're just more interested in allowing you to use it, right? The cross product is going to be a component type calculation, and this returns a vector. So whereas your dot product is a scalar, your cross product is a vector. And the calculation looks like this. Okay, so this is truly a three-dimensional calculation, right? And the cross product, the result, is perpendicular to the plane that A and B lie in, or in which A and B lie. Okay. So if A and B are in the XY plane, then A cross B is going to be along the z-axis. Okay. So there's some deep geometrical reasons why this is true, and again, you'll get there when you get to Cal 3. So I'm not going to belabor this point. This is more akin to being able to get behind the wheel of a car and drive it without understanding why the engine works. Okay, but A and B, or A cross B, also has a similar type of equation that the dot product does, but this time it's the magnitude. Because A cross B is a vector, what we say is that the magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Okay? So if A and B are in the XY plane, and then A cross B lies along the z-axis, what that means is that the magnitude of A cross B is just going to be the length of z, whatever it is. You won't have components. And we'll see that here in just a moment. But you could, because A and B don't have to lie in the XY plane. For our purposes, they generally will, but just in general, because they're generic vectors, they don't have to. Okay. So let's use the same two vectors that we had before. Okay, so this lives in the XY plane just like we had before. It's the same set of vectors that we had before. And now we're going to compute this cross product calculation. So A cross B, and what you should do, by the way, when you have a cross product, if you have components that are missing, just add the missing components. It'll be a lot easier. Okay, so I don't have any k components in either of these. So if I follow this prescription, AYBZ minus AZBY in the I direction. Let me clean up that unit vector. That's a really funky hat. Okay. And then we're going to have AX, this is minus. And do pay attention, okay? I'll say something about these unit vectors here in just a moment, or about this general form as well. But okay, so what you'll notice, this does come from linear algebra and matrices. Okay, so if you haven't had linear algebra or done the determinants of matrices yet, don't panic. I'm not going to require you to do the linear algebra stuff with this. Okay, this is the result. This is all you need to do is then use these components. But notice this first term has a plus sign out front. Now it could end up being negative, but it just generically to start has the plus sign out in front. The second one has a negative sign, and then the third one is plus again. Okay, so this comes from a 3x3 matrix determinant, and when you do matrix determinants, the terms go plus minus, plus minus, plus minus, and so on for however many terms in your determinant you have. And so here we have 3 terms for a 3x3, and therefore it's plus minus plus. Okay, so be aware of that. And then it's just plugging in your components. So this is AX, this is AY, this is AZ, this is BX, this is BY, this is BZ. So then this is just going to be AY is 0, BZ is 0, minus AZ is 0, and BY is 2, right? And of course, this is in the I direction, and that just goes to 0, minus AXBZ, so AX is 2, BZ is 0, minus AZ is 0 and BX is 2, and that is in the J direction. And again, this is going to be 0. And so you can already see that if anything survives, it'll be along the K direction or the Z axis. And so AX is 2, BY is 2, minus AY is 0, and BX is 2, and that is in the K hat direction. Okay, now this is a unique situation. This particular example, the result of our cross product, the magnitude of it is going to be the same as the result of the dot product. Now, this is not a general rule. You can't just compute the dot product and claim that that magnitude is the same as the magnitude of the cross product. But in this case, they are, right? So if we come back up here, we saw that A dot B is 4, and here we see that A cross B is equal to 4K hat, all right? And so if we compute the magnitude of A cross B, this is the same as taking your X component squared, your Y component squared, plus your Z component squared, and square rooting the sum. And of course that reduces down to 4. And so now we can use the alternate definition of the cross product here to solve for the angle, right? So we have A cross B equals magnitude A, magnitude B, sine of theta, right? And we've already calculated magnitude A and magnitude B from the previous example. Magnitude A was 2, magnitude B was 2 root 2, and the magnitude of A cross B we said is 4, and so theta can also be computed as the sine inverse of the magnitude of A cross B divided by magnitude A magnitude B, and in our case this is going to be the sine inverse of 4 over 2 times 2 root 2, which again becomes the sine inverse of 1 over root 2. And once again, if you plug that into your calculator, you will get pi over 4 if you're in radians, or 45 degrees if you're in degree mode. So you can see that both of these give the same answer for the angle, which they should. Okay. So hopefully that gives you some starting sense on how to use the cross product and dot product. Again, we're not going to go into all of the geometry behind it, but I will say this: if you notice A dot B, okay, A dot B is equal to magnitude A, magnitude B times cosine of theta, and the magnitude of A cross B is equal to A B sine theta. So in a sense, you have a number, the same number, magnitude A times magnitude B times cosine theta and sine of theta. So in a sense, A dot B represents the x component of, if I multiply the product of the, or if I multiply the magnitudes together, A dot B, or A and B, not just A dot B, but A and B. If I multiply magnitude A times magnitude B, then the dot product gives me the x component of that, and the cross product gives me the y component. Of the product of the magnitudes. So that's one last interesting thing to note, right? And so there is some deep geometry here, and there's a lot more that we're not saying here. But again, we will leave that for your Calc 3. Again, we just need to be able to hop in the car and be able to drive. We don't necessarily have to understand the machinery of what's going on under the hood. All right. So I hope that helps, and we will see you in the next video.